Okay, so now we can take a look at an application of the dot product. So carrying on from the other lessons from working with the dot product, and now how work is defined. Okay, so work is defined as the product, the magnitude of the displacement traveled by the object, and the magnitude of the force applied in the direction of motion. Okay, so this is again, so the two areas that I highlighted right now are what we've done and what we've talked about from before. This would be U, okay, and then this part in here that we just wrote out, which is the direction of motion, that is what we had as the other vector times cos of theta. Okay, so that's how this is all being defined. So S, a vector is, this case in here is our displacement vector, and that's the direction that we're going in. And F in this case is going to be our force vector, but that will be the horizontal component okay, in the direction of S. Okay, and that was our F cos of theta. Okay, so that's what we're going to be looking at, and that's how we're going to define work, and then we'll use what we've done so far to apply it. Okay, so with our first example here, Max is pulling a sled up a hill with a force of 120 newtons at an angle of 20 degrees to the surface of the hill. The hill is 100 meters long. Okay, so our displacement part of things, if we draw this out, so we've got a hill, it's going in that direction there. He is pulling it here this way. Okay, so that's our F of 120 newtons here. Okay, for the magnitude of that. And then 20 degrees to the hill is what he's pulling, and then your hill is 100 meters. So this is my S displacement vector here, so this would be your S in this case. And then we want to find work, so find the work done. Again, we'll set it up as work is equal to the displacement vector times the F, but the horizontal component of F. Okay? And we do just what we were doing before. So now we take the magnitude of S, and we'll take times the magnitude of F times cos of theta. Okay? And S in this case is 100, and then we end up with 120 and cos of 20. Okay, so just like that. So we've got our two components just like we had before. Now we've just got it set up in a way where this is our horizontal component of our force vector going up this way. Okay, and then that's our displacement vector, and we're multiplying the magnitudes again. Okay, so for this we'll end up with 11,276. This is Newton meters. Okay, because why is it Newton meters? Well, this part in here, that's our horizontal component for our force vector, which is in newtons. Okay, and then this is in meters. Okay, for our units, and that's why we get Newton meters. And what they do with Newton meters, they call them 11,276 joules. Is another way to kind of represent Newton meters. Okay, so that's spelt like that. Okay, so that's our first couple examples there. Okay, so the first example we did was a geometric. These are be algebraic now because we're looking for the work being done in an object moving from, these are points. Okay, so be careful again to distinguish between when we're talking about vectors and when we're talking about points. Those are points. This is a 50 Newton force acting in the same direction as that vector there. Okay, so determine the work done in moving an object from A to B. So this in here, this is defining our S. Okay, because we're moving from A to B. So we want to find this vector AB. And again, we do that. That will give us our S in this case, our displacement. And we're going 8 minus 3, so the 5, and the 4 minus the negative 2. So be careful with those negatives again. And we get 5, 6 for our displacement. Okay? Now, okay, so for right now, what we have is, we have that our force, we want to get it at 50 newtons for the magnitude of our force vector. Okay, but they give us this vector A, which is equal to 3, 4. And we know that the force is just going in the direction of A. So obviously if I do this Pythagorean theorem here, we won't get a magnitude of 50, and that's what we need to get for our vector. So what we do is we'll change this to a unit vector. So first we'll find the magnitude of A, which is going to be 3 squared plus 4 squared, which gives us square root of 25. So the magnitude of A is equal to 5. Okay? So a unit vector then, okay, so to get a unit vector in the direction of 3, 4, okay, then a unit vector okay, and we'll just close this part off here, just like this for right now. You'll see what's working. In the direction of 3, 4, we're going to make it a hat right now, we'll call it that. What we do is we take 1/5 of 3, 4. And if I find the magnitude of that vector, obviously if I take a look, the magnitude of A is 5. And so if we find the magnitude of this whole vector here, A hat, we will get 1. So therefore that means that if I want to get a vector in the direction of A4, but 50 units in terms of the magnitude of it, then my F vector would be 50 times 1/5 and times 3, 4. So like that. Okay, so I've done 50 times of that unit vector, so we would get 10 and 3, 4. Like that, or just 30 and 40. Okay, and you can check. If you take the magnitude of that, you will get exactly what we're looking for, and a magnitude of 50 for that one. Okay, so I just moved over the page a bit, just to give myself a little bit more room here, like this. Okay, so since we have the two vectors, we have both F and S, we have both of them. We can just do the dot product in the algebraic way that we've done it before. So work in this case, not a vector, is equal to my displacement dotted with my force vector, and we have those both now, and we have the components for both, so 5, 6, and dotted with 30, 40, okay, and we can get 150 plus 240 and gives us the 390 joules. Okay, so we can do that now this way because we know what each vector is and what the components are, so we can do the dot product that way. The way we had it before, in the geometric way, we couldn't do this because we didn't know each component like we do now. Okay, so now we'll move on to the next page.